So let's go through an example that shows how the network can self-organize and how overlay edges are established. So suppose that nodes A and B in this example want to communicate through a direct edge connecting A and B, not through multiple hops in the overlay. The general process for creating these edges is as follows. So each node maintains a list of its endpoint resource identifiers. So these are protocol, IP address, and port tuples. And nodes exchange this information through the overlay. So for example, A and B assume that A and B are already connected in the overlay, and we'll see how they can be bootstrapped in a moment. But A sends through the overlay a special message to B that says, I would like to connect to you. And it also sends in that message all the URI endpoints that it knows about itself. B receives this message, and once it knows the endpoints of A in the physical network, it tries to link with them by trying parallel links, in this case to the two endpoints that A sent to B, the UDP and the TCP endpoints. Concurrently, it sends a message over the overlay, because at this point it does not have yet a direct link to A, but it does have a path through the overlay. And it sends its endpoint URIs back to A, so A can try to link to B through the physical network as well. So when A receives this reply from B, it initiates linking over the physical network, trying again in parallel the identifiers that B has sent over the overlay. And if it receives a link request from B, it sends a link reply. So there's a protocol to determine that the two nodes have reached a consensus that they have a link, and at that point a direct edge between A and B can be established. Now, this simple process works as long as A and B are in the network, so there's the question of how do A and B join the network, how do they bootstrap? And there's also the question of what happens when A and B are behind nets. In the more general case, when both of them are behind different nets. So bootstrapping new nodes actually uses the same approach that was described now, but with an added step, which is, let's say that a node wishes to join the network, and this is the node with my IPOP ID here to the right of the figure. Before it bootstraps into the network, it needs to form the so-called leaf connection, which is a temporary connection with a node on the public network. And this leaf connection is used for the node to bootstrap itself into the overlay. It also is used for the node to discover its public endpoints, the URIs. For example, if it's behind the net, it can discover by querying the public node, what is the address that you see for me? You can see, you can discover its net mapped URIs. But given that a node finds bootstrapping public node to be its forwarder, what it does at that point is the same process we saw earlier. It sends a connect to me message, but this one message has a special behavior. It's sent to its own identifier, so this message will go towards the identifier that the node is trying to join the network with. But there's no node with that particular identifier in the network, so the message is actually delivered to the immediate left and right neighbors of the node, which is essentially begins a process for these other two nodes to establish edges with the node that's bootstrapping itself. And basically that's the initial requirement for a node to be routable in the overlay, that it has both left and right neighbors. And once it acquires left and right neighbors, it can begin acquiring the far edges and be able to route messages efficiently over the network. But the process begins by sending a connect to me message to itself, that message delivered to left and right neighbors, and the near edges to the left and to the right are established through the process that we saw in the previous slide. Now, what happens when A and B are behind NATs. So supposing this example, we have A and B constrained by NATs, and we're going to use these NATs M and N with these example IP addresses to illustrate what's going on. So the first thing that happens is A and B send messages over the overlay with the URIs. And the assumption is they have already been bootstrapped, and so they are routable through the overlay. And in these messages, the URIs that A and B send include URIs that A and B discovered in the process of bootstrapping into the network. So when A contacts a public machine on the network, the public machine will see the NAT mapped address, and it can tell A back on the reply, this is the address that I see for you. And A keeps that information locally. B does the same thing. So let's assume that these are the NAT mapped addresses for A and B are M, IPM port X, and IPN port Y conversely. Now, once A and B exchange these connect to me messages, they're going to begin the process of linking. So B received information that says A has one of its URIs on IPM and port X, and it's going to send a message to MX using, in this example, we're using the UDP protocol. So that message goes through B's NAT, and it is translated by B's NAT, so it goes out as source NY, destination MX. And in the process, it creates a mapping in the NAT that says, if I receive a reply from MX, it's okay for that reply to go through the NAT and to be delivered to node B. Now what happens at the destination is that before A ever sent a packet to B directly, the NAT on A side is not aware that B exists, so to speak. And it doesn't have a mapping for MX received from NY, so it's going to drop that packet. But that's okay, because A concurrently is trying to link to B. So it's sending a message with the destination NY, which is the NAT mapped address that it received during the connect to me request. That goes through the NAT on A side, and as a side effect, it creates a mapping, NY to MX, and that's called a hole. That's why this technique is referred to as hole punching. That's a hole in the net. So the message gets translated, and it goes out to NY, and because B has sent a message to A before, that message is allowed by the NAT. There's a mapping, a hole punch mapping here, and the message is delivered to B. Now if B retries a little later to send the same message that it did before to A, this time around, because A has also sent a message to B, the message is delivered. And at that point, A and B have a link, and they can use this link, this edge, to communicate directly over the physical network. Now there are some challenges that need to be addressed once you have these NAT traversal. You have to keep these connections alive, otherwise these mappings can disappear from the NATs. They are ephemeral and they can be reassigned. So it's important to manage these connections, these edges, also once they are established. And there are cases when NAT is not traversable in this fashion. NATs that are not of the type cone, this technique will not work. And we need to find alternatives to deal with this problem. And part of this discussion is in the next unit when we talk about performance enhancements.